So it really is my pleasure to introduce Kendra tonight, Kendra Murray. She is a geologist who uses geochemistry along with fieldwork and numerical modeling to study the many magmatic, geomorphic, and tectonic processes that change rock temperatures, such as wildfires, volcanic eruptions, all the way to the building of mountain ranges. Much of her active work is focused on the geodynamic evolution of the U.S. Intermountain West from the Proterozoic to recent times. She also has an ongoing interest in active learning in geoscience classrooms, which is a good thing since she's a teacher. Kendra received a bachelor's in geology from Carleton College and a master's and PhD in geosciences from the University of Arizona. She was a postdoc research fellow at the University of Michigan and a visiting assistant professor at Hamilton College prior to joining her current position, which is at the faculty at Idaho State University, which she joined in 2019. So without further ado, Kendra, it's yours. I'm looking forward to this talk very much.
Thank you so much. I'm going to go ahead and share my screen, get my slides organized here. Move a few things around on Zoom. All right, well, it's my great pleasure to be here, and I really want to thank the organizers for inviting me to speak. I was really thrilled to get the invitation. And I want to give a special thanks to John for crafting this awesome photograph to help me motivate my talk today. I also want to acknowledge that much of the work I'm going to be talking about today was done while I was at the University of Michigan working with Nathan Nemi and Maureen Clark. And then I'm also going to be looking ahead a little bit at some work I hope to do with my colleagues both at ISU and Montana State and Columbia. All right, so today I'm going to describe how we can use the field relationships shown in this photograph to probe the ancient history of our region. Here we're looking at the Flathead sandstone, which was deposited in Cambrian time on top of ancient igneous and metamorphic rocks. And these igneous and metamorphic rocks I'm going to generally refer to as basement rocks. They formed at high temperature deep in the earth a long time ago, and they're commonly covered in sediments like this. The surface between these two rocks represents an enormous amount of time, and such gaps in the rock record are commonly called unconformities. This particular relationship, where we have Cambrian sediments sitting on top of basement rocks that are much, much older, is observed not only in our part of North America, but across the continent and indeed on every continent on Earth. And because it represents such a profound gap in time and is found so commonly on the Earth, we call this feature the Great Unconformity. One of the most famous exposures of the Great Unconformity is in the Grand Canyon. You'll see on this diagram that the time here, it's not quite as big of a gap in time as we have in the Tetons. It's only at most about 1,200 million years. But remember, multicellular life has only existed on the Earth for 600 million years. So just the amount of time that we're talking about here is truly immense. In this diagram, you can see there are a bunch of these red squiggly lines. And this is showing us that actually unconformities are really common in the Grand Canyon section. There's a lot of time missing here in different places. And indeed, in the rock record, this kind of missing time is very common basically everywhere that you look. We can visualize this missing time in a diagram like this on the right side of my screen here, where the colors indicate the time periods in Earth's history where there is a rock record in the Grand Canyon, whereas the black areas are the time that's not represented in the rock record. And we don't know what was happening during this time because we don't have rocks that tell us about what was happening in this part of the world at this time. For hundreds of years, geologists have understood that most of Earth's history is just not preserved in the rock record. The rock record is very incomplete. This is an illustration of a major unconformity that James Hutton made observations of and reported on in his monograph, Theory of the Earth. Since Hutton's time, we've known that the incompleteness of the rock record reflects back at us these huge gaps in our knowledge of Earth's history. And even today, with all the tools that we have, it's easy for us to think that this lack of a rock record just presents an intractable problem. There are just some parts of Earth's history we're never really going to be able to access. In the last 5 years or so, I've really changed my perspective on unconformities like the Great Unconformity. And now I don't view them just as gaps in knowledge that are intractable, but actually as tools that we can use to leverage a combination of field observations and geochemistry to learn about these gaps. And we're going to use the geochemistry of the basement rocks themselves. These are the rocks that experienced all of this missing time, and they contain an archive of what happened if we know where to look for it. So I hope to convince you today that we now have the ability to start accessing parts of this archive. To do this, we're going to travel to Colorado's Front Range, which is a part of the Laramide province, just like the Teton Range. And the Laramide province is this region of North America that experienced mountain building between about 80 and 45 million years ago. You can see in this diagram on the left side of my slide that these ranges are bounded by major faults, and they tend to be cored by big exposures of these basement rocks. So the Wind River Range in Wyoming is one of the classic examples of one of these. One of the persistent questions about the Laramide province is why mountains were built in this part of North America at this time. Because at this time, kind of like today, the plate boundary was located very far away to the west. And normally it's at the plate boundaries where we expect mountain building to occur. And so we're curious about why the Laramide province kind of is where it is. One of the prevailing hypotheses about this is that this pattern of mountain building, the spatial pattern, actually reflects or maps out an ancient continental rift system. Specifically, the rifting of the supercontinent Rodinia. So Rodinia was the supercontinent that existed before Pangaea, and it was rifting apart kind of in several phases over about 300 million years at the end of the Proterozoic, during a time that we call the Neoproterozoic. This is one of several possible reconstructions. For the purposes of my talk today, we're not really all that interested in where Australia and Antarctica were relative to North America, but I do want to point out here is the future Laramide province. The evidence that we have for rifting is contained within a bunch of sedimentary basins that are bounded by faults that are mapped out in purple here. And then also I'm going to be referring to North America in the deep past as Laurentia. If we take our cross section through the Wyoming part of the Laramide province, we can get maybe a better sense of the idea of this hypothesis for the origin of the Laramide. All right, so we have a cross section here, and what you can see is today we have our modern mountain ranges like the Wind Rivers, for example, and they're bounded by these high angle faults. The proposal, the hypothesis, is that these faults have their origins as faults that formed during Proterozoic time as a result of the stretching of the crust that accommodated the breakup of the supercontinent. And then they were reactivated more recently, perhaps several times since the Proterozoic, and then contributed to building the topography that we know and love today. So this is a geologically compelling idea. It makes sense that once you break a rock and you create a plane of weakness, that you'll just kind of activate that structure rather than breaking a whole new fault somewhere else. But it turns out that this is a very difficult idea to test with the geologic record. And the main reason for this is that if you're calling upon reactivation of these structures over and over again, you are calling upon processes that overprint and remove the evidence of the earlier geologic history of these structures. This idea of reactivation is sometimes called inversion tectonics, but it's by its nature is kind of difficult to study because it doesn't leave a lot of evidence in the rock record. The solution to this problem that I'm going to show you today is that events and processes in the deep past leave a temperature imprint on the basement rocks that experience this reactivation history. And this is a temperature history that we can retrieve using the types of data that I'm going to show you today. Right, so today we're going to look at some data that support the idea that the Front Range, which is the largest of the Laramide ranges, has its origins as a Neoproterozoic rift basin. The reason that we can do this is kind of twofold. One is the importance of unconformity relationships. The great unconformity is present in the Front Range, and it tells us that our basement rocks were in the near surface at multiple times in the past, and this turns out to be very important. The other thing is that in the last decade or so, our ability to interpret the geochemistry that I'm going to describe to you in these really ancient rocks has blossomed. And we now have the ability to see into the Proterozoic in ways that we didn't have before. So the methods that I'm going to be describing today are, broadly speaking, geochronologic methods. And so geochronology is the way that we use the natural decay of radioactive isotopes in minerals as a clock to tell time. The type of geochronology that I do is called thermochronology. And as the name suggests, it tells us about the temperature and the time history of rocks. If we can document the timing and rate of processes that change rock temperatures using these tools, we can then think about things like burial and exhumation in the past. The systems that I am an expert in are considered low temperature thermochronometers. Kind of depends on your perspective. But the systems that I use are sensitive to changes in rock temperature up to about 300 or 350 degrees C, so in the upper part of the Earth's crust. We can use changes in rock temperature to tell us things about burial or erosion because of the geothermal gradient, the fact that it gets warmer as you go down in the Earth. So for example, this is a schematic cross-section through the upper part of the Earth's crust over some horizontal distance. And the colors here indicate how the temperature changes with depth when it's in equilibrium with some periodic topography imposed on the Earth's surface. So when rocks are buried, they heat up. And when they're exhumed, and by that I mean when they move towards the Earth's surface, either because of erosion or perhaps along a fault, they cool off. The particular type of thermochronology that we're going to spend time with today is called uranium, thorium, helium thermochronology. So uranium and thorium are the elements that decay. They are the parent isotopes. And helium is the daughter product of that decay. Now, some of you might be familiar with a radioisotope system where uranium decays to lead, and the uranium-helium system is directly related to this. And this is because when uranium decays to lead, it actually experiences a whole series of intermediate decays with intermediate parent and daughter products. And when an alpha decay occurs, an alpha particle is emitted, and this is 2 protons and 2 neutrons. Ernest Rutherford named this an alpha particle back in the day. But this is also a helium-4 atom. And so in this way, helium is a daughter product of this same system. And both naturally occurring isotopes of uranium that are radioactive produce helium, as well as the decay of thorium-232. Now, as a helium person, I like to remind people that actually the uranium-helium system was the very first geochronometer ever proposed in the very early days of our understanding of radioactive decay by Ernest Rutherford. So he basically said, well, if we know the rate at which helium is produced and we know how much uranium there is in a material, we should be able to calculate how old that material is. And this idea was tried with multiple different radioisotope systems, not just the uranium-helium system. And some systems, like the uranium-lead system, where lead is the daughter product, it seemed to yield ages, even in these really early days, that made sense geologically, based on what we already thought we knew about these rocks. However, the helium system yielded ages that were far too young to be reasonable as formation ages of material. Now, these early geochronologists, they were great chemists. They knew that helium is a tiny, noble gas. It's non-reactive. It was probably just leaking out of these materials. But for most of the 20th century, we didn't actually know what the process was that was responsible for this leaking. And therefore, we didn't know what the meaning of a helium age was. What was it actually telling us about? Maybe it would be used occasionally for specialized applications, but not much more. This started to change in the 1990s. And today we know that helium loss from minerals is a temperature sensitive process. And it's governed by this process in particular called diffusion. And we have a good mathematical description for diffusion, which is great. There's been a lot of experimental work done since the 90s, characterizing the kinetics and mechanisms of helium diffusion in a bunch of different minerals. And this has finally transformed helium thermochronology into a tool that's useful for geologists. So these thermochronometers, they're temperature sensitive, right? And I'm going to be describing their temperature sensitivity using this concept called a closure temperature. And you can think of a closure temperature as the temperature below which helium, in this case, doesn't leak out of the mineral anymore. So at high temperature, the helium has a lot of energy, and so it can leak out of the mineral immediately upon its formation. At low temperature, once the helium forms, it gets trapped in the mineral and the clock starts ticking. It starts accumulating. Closure temperature is really just a useful shorthand for all these kinetics and mechanisms of diffusion, but it's a really useful one for us geologists who want to connect cooling ages to process. So here we are in 2022, and we have a whole range of geochronometers and thermochronometers with different temperature sensitivities that are available for us as tools to study the Earth. We call the high temperature systems the geochronometers. These are the ones that tell us about rock formation and metamorphism. And so, for example, if you want to know the crystallization age of a granite, you'll use a geochronometer to do that because the clock starts ticking when the crystal forms. On the other end of this array of tools, we have the low temperature systems, the thermochronometers. And these are telling us about rock cooling. And so they're sensitive to much more near surface process. As I said, things like erosion and burial, but also wildfire, meteor impacts, volcanism, really anything that changes rock temperatures over a sufficient amount of time can be documented by these systems, which is the reason I think that they're really cool. The system that we're going to spend the most time talking about today is the helium system in the mineral zircon. So this has a pretty wide range of temperatures it's sensitive to, between about 140 and 330 degrees centigrade. If you convert that temperature range using a normal geothermal gradient to depths, these systems will document cooling from about 4 to 12 kilometers depth up to the Earth's surface. This is the system where there have been some really important advances in our understanding of some of the complexities of the system, which we will talk about. And it's really become a workhorse for those of us who want to study the deep time of rock history. I'm also going to mention in passing some apatite, helium, and fission track data, and then a higher temperature biotite argon system as well. But these are all considered on the lower temperature end. They're telling us about the cooling off of rocks. All right, so in order to do this work, we go into the field and we collect pretty big samples because although the minerals that we use for geochronology, like apatite and zircon, are pretty common in most of the rocks we work in, they're not very abundant. So we need a lot of material. And we take that back to the lab and we crush it down to a sand size, and then we use a variety of density and magnetic separation techniques to isolate the individual minerals that we're interested in. So here's an example of a photo taken at very high zoom under a microscope of individual apatite crystals that we're getting ready to date. So what we do is we pick these individual crystals with these tiny little tweezers and we measure their dimensions. And then under the microscope, we put that little crystal into a little foil packet. So it's kind of like we're making apatite or zircon ravioli. And then we take that packet and we take it to the lab, basically. And the first thing that we do is we hit the packet with a laser, and the laser heats up the packet and the crystal inside, and the helium degasses from the crystal, and we use a mass spectrometer attached to a vacuum line to measure the amount of helium that's there. Then we take each of those packets and we dissolve them in acid and we spike them with some isotope spikes. And then we use a different mass spectrometer to measure the abundance of uranium and thorium in each crystal. At the end of this process, we've measured the abundance of helium, our daughter product. We've measured the abundance of uranium and thorium, our parent elements. And so we know the decay rates based on work done by our physics friends. And so we can calculate how much time has elapsed since that crystal started holding on to its helium, since it was cold enough to do so. However, with these types of cooling ages, that's actually just where the fun begins. Because in order to understand what a cooling age is telling us, we need to take into account the geology that we know already, the kinetics of helium diffusion, as well as the data. And so we use numerical models to help us bring all of those things together. So I'm showing a screenshot here of one of the models that I commonly use, which is called Hefty. All right, so let's talk about some geology. We're going to use thermochronology today to document the deep time history of some basement rocks in the Front Range, as I said. There's been quite a bit of previous thermochronology that's been done in the Front Range. A lot of this has focused on the laramide history of this mountain range, kind of the most recent tectonic event here. This map that I have on my slide is showing a simplified bedrock map, showing there's a lot of Proterozoic, igneous, and metamorphic rocks here. Some work has also been done using these rocks as kind of a natural laboratory to think about how these helium thermochronometers behave in really old rocks. Today, we're going to explicitly target the Neoproterozoic history of these rocks. And since I've started to do this work, other people have also been working on these rocks, and there's some interesting studies that have come out of the Pikes Peak area down here. I'm not going to talk about those explicitly today, but I'd be happy to take questions if anyone's familiar with these studies and would like to know a little bit more about how they compare to mine. All right, so let's go ahead and zoom into the study area. We went to the Front Range just outside of Boulder, Colorado, shown here. And we collected several sample transects. So we have one up near the Continental Divide at high elevation, which I'm going to call the range interior samples. And then another transect of samples taken at much lower elevation down near the front of the range, which I'm going to call the range front samples. The grade unconformity is present here. So you can see right close to the range front. And here we have Permian rocks that are deposited on the grade unconformity locally. All right, so I'm going to show you some data now. And what I'm going to do first is show you data plotted on an elevation versus crystal age plot. And so we sampled over about 2.5 kilometers of elevation in this study. And so our range interior samples are at high elevation, our range front samples are at low elevation. Right now, I'm plotting all the individual apatite crystals that we dated from this study. And you can see that all of them have pretty uniform helium ages, right around 54 million years, plus or minus 7. And so these thermochronometers are telling us about the most recent part of the history here, the laramide. So the recent cooling related to the formation of the Front Range as we know it today. Next, I'm going to overlay our zircon helium data. And I'm going to just do it for the range interior first. So here are those individual crystal ages. You'll notice that those ages, they're older than the apatite helium ages. And this is what we expect based on the relative temperature sensitivity of these two systems. The zircon helium system, it closes at higher temperature. And so if our rock is approaching the Earth's surface, the clock is going to start ticking in that system first. And so the ages are going to be older than the apatite helium system. If we want to include our range front data on this plot, I need to actually expand the x-axis pretty dramatically because there are multiple samples here that have much older zircon helium ages, including individual crystals that are Paleozoic and even Neoproterozoic in age. So what I'm going to do next is I'm going to tell you why it's possible that individual crystals from the same sample, the same piece of rock, it's about the size of your fist, that all have the same thermal history, can have such radically different ages. You know, how can crystals with the same history have Neoproterozoic age and a Cretaceous age at the same time? In order to answer that question, I need to tell you a little bit more about how helium thermochronology works. All right, so we talked about how these data are not only a function of time and temperature, but they're also sensitive to the composition, the chemical composition of each individual crystal. And this is because when the decay of uranium and thorium happens in these minerals, that decay causes damage to zircon's crystal lattice. This damage in zircon creates fast pathways for helium to diffuse out of the crystal. So we have our helium atom, it's randomly walking around the crystal, and then it hits one of these zones, and it's like a fast highway out of the crystal, and whew, it can leave the system much more quickly than it would have been able to otherwise. The other thing that's important about this damage is that it itself is temperature sensitive. So at high temperature, when this decay happens, the crystal lattice heals itself, or what we call annealing, very quickly. And so the damage doesn't accumulate. Whereas at low temperature, every time one of these decay happens, the crystal becomes more and more damaged. In our current models of how this works, the rocks need to get above about 240 degrees C to completely heal radiation damage on geologic timescales. So the result of this complexity to the system is that we have a coevolution of radiation damage and helium diffusion in the mineral zircon. The more damaged a crystal is, the less helium it can hold on to, and therefore the younger the age is that we measure. We have an empirical model for how this works. It's based on some very meticulous laboratory experiments. And so we pair that with looking for these types of effects in our data sets. And the way that we do that is we use a parameter that we call effective uranium, or EU, as I'll call it. This is just a combination of the amount of uranium in our crystal and the amount of thorium in our crystal, and then it's scaled by the helium production of these two things. So thorium doesn't produce nearly as much helium as uranium. This is essentially a proxy for radiation damage. So we're not measuring the damage directly, but we're looking for evidence for it in our samples. All right, so what does this actually look like? Well, show you that. I'll show you a few simple thermal histories of rocks. So on the left here, we have a temperature versus time plot. You can tell I'm a geologist because I have temperature going down, like we're going down in the Earth on the y-axis here. This yellow zone here is the temperature range over which the zircon helium system goes from being totally open and losing all of its helium to being totally closed and hanging on to all of it. This is what we call the partial retention zone. And then this blue line is a hypothetical time temperature history a rock might experience, where it sits at relatively high temperatures for a long period of time and then exhumes rapidly at about 50 million years ago to the Earth's surface. In this kind of very simple thermal history, we expect every zircon crystal in our sample to have a 50 MA age, the same age, no age variability. So if we were looking at our data and we were plotting the age that we measure against this effective uranium parameter, the abundance of uranium and thorium, we would expect just uniform ages. However, if we have a sample that has a more complex history, we expect a negative slope relationship between age and EU. So in this green path, our rock approached the Earth's surface 500 million years ago and then sat at the surface for hundreds of millions of years, differentially accumulating radiation damage and helium, and then experienced a thermal event, burial and exhumation, for example, let's say 50 million years ago. And we get this extreme amount of age variability in the same sample as a result. So our grains that have a lot of uranium and thorium in them, they're really damaged and they can't hold on to their helium very well. And so they have young ages that at face value are telling us about this cooling event around 50 million years ago. And then the low uranium and thorium grains, they're less damaged. They hold on to their helium way better. And so they have older ages as a result. And at face value, these ages are telling us about this much earlier history. And so in this way, when you have a sample that has a wide range of ages and it has a trend like this, we get really excited because what it means is we have a much more sensitive chronometer. There are far fewer specific histories that can give us really young ages and really old ages in the same sample. So our ability to take what appear to be very complicated data sets and interpret them geologically. This is what has transformed our ability to measure the thermal history of ancient rocks with complicated histories. If we return to my data set, instead of looking at this elevation versus age plot, which really isn't telling us very much, if we just take the zircon helium data and we make one of these age versus EU plots, there are a couple things that we can see right away, kind of qualitatively. So the first is that there's a beautiful negative slope relationship between age and EU here. And this, at least at face value, is consistent with our model for how this works. We also see that there's some spatial variability. So samples in the range front and in the range interior, in the red and the blue respectively, have different trends over the same compositions, which suggests that these samples probably have histories that are different than each other that we can resolve using these data. And then finally, we have a bunch of old ages, right? Ages that predate the laramide by a lot. And so this suggests that these data as a whole might offer us new information about the pre-laramide, the much earlier history of these rocks. So what I just described is kind of a first pass at what might be going on here. But the next thing that we do is we actually want to do a quantitative test of whether our understanding of these systems seems to make sense. And so we're going to use a thermal history model to do that. All right, so whenever you use a model like this, you always want to have some solid questions or hypotheses that you're testing. In this case, generally what we're trying to do is we're asking what thermal histories could produce the observed trend that we have in our data. And of course, we're always looking to learn something we don't already know about our rocks, right? These models combine the geologic record in the study area that we know independently of our data, and then we make some decisions about how to actually design the model and what kinetics we're going to use, things like that. So let's talk about the geologic record in this area first, because we actually know a lot about especially the more recent history of the Front Range, which is one of the things that helps us see further back in time. So here I'm showing again another temperature versus time plot on the top part of my slide. I mentioned that the rocks that we sampled, they formed 1.7 billion years ago, and so that's where we start the model. I'm not showing that here though. Previous work that's been done on these rocks using kind of middle range thermochronometers, they tell us that these rocks have been colder than about 280 degrees C since about 1400 million years ago. And so that's a really important constraint. That basically puts an upper bound on how hot our rocks could have been since that time. I'll also note that we know the surface temperature today. So this is a typical piece of the Boulder Creek granodiorite, which is the basement rock that we sampled. But if you wander around in this part of the Front Range, you'll see another rock that's much weirder looking. So this is a photograph of what's informally called the Tava quartzite. And these have been observed in the Front Range since the late 19th century. And it's clear from the textural evidence that you can see in the field that these are sandstone dikes that were emplaced down into the basement rocks. And so they're strange rocks. In our part of the Front Range, they are located up here near the Continental Divide. And so what we know about the Tava is that it's associated with mapped faults. As I said, it has both structural and sedimentary textures that suggest that it was forcefully injected into the crystalline basement. And that injection might have been driven by something like gravitational loading, perhaps by ice or by other sediment. Maybe there was some seismicity involved. We don't really know exactly what exact process might be responsible for it, but from our perspective, there are a couple important things about this observation in the field. So this type of sand remobilization, it requires a sandy fluid, not a rock, right? So it means that we had sand sitting on top of our basement rocks when the Tava formed. And this stuff, it really can't penetrate down more than about 1 kilometer into the host rock based on observations of these features in other places. And so this is a really important constraint for us because it tells us our basement rocks that we sampled were in the near surface and cold when the Tava formed. So how old is the Tava? Well, we have a couple different lines of evidence. One is that if you can look at the detrital minerals in the Tava sand, and they are dead ringers for other sedimentary rocks that are deposited across Western North America in Neoproterozoic time. Like here in Pocatello, I'm sitting on the Pocatello Formation. It's one of those rocks. It looks just like that, has the same fingerprint. There's also been some direct dating of veins that cross-cut the Tava dikes that also support a late Proterozoic, a Neoproterozoic age for these formations. All right, so if we return to our time versus temperature plot here, we're going to require our basement rocks to be within about 2 kilometers or 60 degrees of the Earth's surface at the time when the Tava formed. Another really useful thing about the Tava Kiev is that its preservation, the fact that we can actually see it in the field today, means that we haven't lost very much of that basement rock since it formed, or else it would have eroded away, right? And so at 2 other times in the history of the Front Range, when we have evidence that the basement rocks were in the near surface with sediment accumulating on top, we know that this same constraint holds, and we need our rocks to be back at the Earth's surface in the early Cambrian, as well as in the late Paleozoic during the ancestral Rocky Mountain orogeny too. We know a lot about the Paleozoic and Mesozoic history of these rocks based on stratigraphic sections that are still preserved in the Denver Basin and around Colorado, including locally in the study area. And these tell us that these rocks have been in the near surface for most of the Phanerozoic, except for right before the Laramide. The Pierre Shale was deposited. That's a very thick sedimentary unit, and that buried these rocks pretty substantially right before the Laramide orogeny. So we know a lot about this part of these rocks' history, but we have these really big gaps, right? These are what's represented by the great unconformity. And so what we're going to ask the model to do is to explore those time periods. And we're just going to put an upper temperature bound because we know these rocks didn't get so hot that they reset the argon-argon system in biotite, which is where the upper bound on these boxes is coming from. Right, so I'm mostly going to show you the results from models of the Front Range or the range front samples. And so what we're doing here is we're trying to reproduce this age EU trend in these samples. And so we're putting in representative crystals from the zircon helium system. We're also including apatite helium ages as well. And then finally, we make some choices about other things related to the modeling. So we choose a modeling program. In this case, I'm using Hefty. And then we make sure to select the kinetics for helium diffusion that include this radiation damage complexity. And then what this program does is it does what's called a Monte Carlo search of time, temperature, space. And so we run the model to find at least 100 good fit paths that fit our data. And so this Monte Carlo search, it generates individual time, temperature paths that go through all of these boxes and then predicts what the age pattern would be, compares that to our observations and gives it a yes or a no. So what this looks like if you're actually running one of these models, is like this. So you can see the model is testing different time temperature histories and it's just saving the ones that yield a good fit. Once we've completed a model run, we can visualize the results like this. Here's our now familiar temperature versus time plot. You can see the boxes that I described to you, including these 3 very important near surface constraints. And then here's a fit to that AGU trend if you're interested in that. So the thing that I'm most excited about in this model result is what's happening here in the late Neoproterozoic. It appears that this model, the combination of the geology and the data, require a heating event at this time, a pretty significant one actually. So we're looking at here is the peak temperatures and the dots, and then you can see the paths related to those temperatures here. They peak at about 230 to 285 degrees C. And this heating event is happening in the late Neoproterozoic, so after the Tava formed, but prior to deposition on the Great Unconformity during the Cambrian time. I also mentioned that this is a long thermal event. These rocks had to be hot for at least 16 million years, and for most cases, much, much longer than that, in order to do what they need to here. So what do they need to do? Why do we have this heating event in our model results? Well, what this is telling us is that we needed at this time to completely reset the zircon helium system. All the helium gone and all the radiation gone in our zircons, and that requires this kind of event at this time. One thing I'd like to note is that the magnitude, how hot these rocks needed to get at this time, is pretty well constrained by the data. However, the exact timing of when the rocks became hot and for how long actually depends on how you decide to put the geology into the model. It's not something that's coming out of our data. So here again is our, what I'll call the preferred model, has all three of these constraints. But let's say you're a little skeptical of how well we know how old the Tava is, and we want to expand our Tava box. We still need a heating event after this time, but when it actually happens is not very well constrained. Similarly, let's say you say, well, Kendra, there's not actually any Cambrian sediments sitting on the Great Unconformity right in Boulder. It's actually just these Permian rocks. So what happens if you relax that requirement? Again, you still need a heating event. Just when it happens, expands even further. The other thing that I want to just take a moment to point out is that, we have a bunch of different samples, right? And so the range front samples show this story. But if we go up to the continental divide and the range interior, we don't see this heating event. So here's a side-by-side comparison of just that part of the model and a couple samples from the range interior. And the reason we think this is the case is that these samples up near the continental divide, they got hotter during the Cretaceous. And so we think that the preservation of this signal is spatially controlled by exactly how hot things have subsequently gotten. Now, these rocks in the range interior, a model result like this, it doesn't say that these rocks couldn't have experienced Neoproterozoic heating. It just says that they could have been hot or they could have been cold during the Neoproterozoic. They just don't document that part of the history very clearly. All right, so we've talked about the thermal histories here, and now we get to actually start thinking about the geology again. So what process could be responsible for heating up rocks during late Neoproterozoic time in this part of the world? Well, we think that the simplest explanation for a prolonged heating event of this magnitude is to take our basement rocks and to bury them in a basin. And as we've already discussed, at this time in this part of North America, rifting was happening. Rodinia was in the process of slowly falling apart. There were several different periods of rifting. But as I've already described, although there's abundant stratigraphic and structural evidence for rifting in the western part of Laurentia, as you move east of the Uintas, we don't have that stratigraphic record. We just have the Great Unconformity, where we have Cambrian or younger sediments sitting on basement. Except in the Front Range, we have this Tava quartzite, right? So we would argue that the Tava itself, independent of the thermochronology, actually supports that this area was an extensional or rift setting. And that's because the Tava requires that we had sediment being deposited in Neoproterozoic time. And so for that, you need a basin. And then the rapid extension and sedimentation that you expect in a rift basin, this is exactly the recipe that you need to create one of these kind of injectites, right? To remobilize sand down into the basement. And in fact, if you go to the other side of Laurentia, when Rodinia was breaking up, there are other basement-hosted clastic dikes observed that are in clear association with intercontinental rift structures that support this idea for the context of the Tava being formed in a rift basin. So we think that we have pretty good evidence for burying the basement rocks that are now in the Front Range in a rift. And so the way this would work, we think, is that the range front, what is now high topography, would have been in the basin of the rift. So it's kind of like in Jackson Hole, you know, you're down in the basin, and the basement rocks under you would be where the basement in the Front Range was during Neoproterozoic time. Because we have a temperature estimate of how hot these rocks got, we can convert that using a range of geothermal gradients that we think are reasonable to how much sediment would have been required to bury and therefore heat up the rocks this much, which is between about 3 and 9 kilometers, depending on how hot you think geotherm was and how close you think our samples were to the protosurface. Now, because of how normal faults work, if you know how much sediment was accumulated or how much throw on the fault there was, that tends to scale with the length of the fault in map view. And so a fault of this magnitude would be substantial. It would probably be tens to hundreds of kilometers long. And so we think that this is compelling evidence that the Front Range has its origins as a Neoproterozoic rift feature. And indeed, it probably marks the easternmost extent of Rhodinian rifting into Laurentia. All right, so I think that our idea for how these rocks got hot at this time is pretty compelling. However, our interpretation requires that these rocks, these basement rocks, came all the way back up to the surface by about 500 million years ago. And so we need some mechanism to do that. We need to remove all of that sediment that we're calling upon to bury the Front Range in the first place. And you know, that is much less certain in terms of what might be going on there. And so there are a couple of different possibilities I want to throw out. So one is that if we look at other examples of going from rifting of a supercontinent into the development of a passive margin, for example, the Atlantic margin that formed as Pangaea broke up, we can see that that rock record is more complete. We know more about it. There are actually kind of vertical motions at the kilometer scale at those passive margins that significantly postdate rifting. And so it's possible that maybe we're seeing those similar processes play out along the Rhodinian or the Laurentian margin. That's a newly formed passive margin about 500 million years ago. I also want to point out that the Front Range, its location corresponds to the development of this feature that's called the Transcontinental Arch. This is a regional drainage divide, and it's inferred from the sedimentary record because it seems like around this time, all the sediment that was coming off of eastern Laurentia off of the Grenville orogeny, it stopped making its way all the way over into western Laurentia. And so sedimentologists have called upon a divide. And so it's possible that whatever process was responsible for forming that divide is the same thing that was exhuming the Front Range region back up. So basement was exposed again. Another possibility is that it's not a tectonic process at all, but it's something related to glacial erosion. And this is because at this time in Earth's history, there were periods when there was significant continental ice sheets at low latitudes on the Earth for millions of years. This is a hypothesis called Snowball Earth. There were probably multiple periods of this in late Neoproterozoic time. And it's been recently proposed that the Great Unconformity is actually a product of some global scale erosion event related to these glaciers that removed about 3 to 5 kilometers of material on average from most continents. Now, the magnitude of exhumation here is what we're calling upon. That's what we're looking for, a process to explain that same magnitude. And so it's possible maybe this is a signal that we're seeing in this area. However, before we get too excited excited about solving this problem, I want to remind us that we actually don't know the timing very well of our erosion event, or our event that's bringing the basement rocks back up to the Earth's surface, right? So we know the magnitude well, but we don't know the timing, which means it makes it difficult for us to attribute that part of the history to a specific process. And we need more geology. We need more information to help convince us, okay, well, I think this is what's going on, but another geologist might think that this is a more reasonable situation, or this one is too. And so before we make some definitive statements about what might be happening after this heating event, we need more information. So to summarize my story about the Front Range, I hope I've convinced you that thermochronology is this really cool tool and allows us to do things like connect a laramide mountain range to its origin as a neoproterozoic structure. And also that we need to be careful about what we're actually learning from these data sets. In this case, we need better time constraints, probably from the geologic record, to better attribute the kind of rock cooling part of this history to other processes. And so here are just some cartoons about both of those things. The last thing I'll say about this study is that, kind of wrapping back around to the great unconformity, one of the reasons we can do any of this is because we have this very special observation that our rocks were in the near surface at multiple times and they were cold. And so that then sets up the need for a heating event like this. All right, so I told you I would bring this back to where we are here in the Northern Rockies. And what I'll say is that we have abundant great unconformities exposures in this part of the world where we are, just waiting to be studied in more detail. So here's a kind of a classic great unconformity exposure, kind of the outcrop scale near Dillon. If we take a look at a geologic map of our region, we can see that we have where these blue rocks are in contact with red, which I'm using as basement here. These are our great unconformity exposures. This is the Teton Range, for example. And just like in places like the Grand Canyon, we have these huge gaps in our knowledge. And although we generally know some of the main regional events, when we dig right down to it and we go to a place like the Tetons, we're still missing just an enormous amount of time, right? Where we have more than 40% of Earth's history is just not represented by the rock record here. But we do have the basement rocks, which were sitting at the Earth's surface, for example, when the Cambrian flathead was deposited. And so by sampling near it, we'll be able to learn more about this history. And so in the Tetons, we have lots of interesting questions about what was happening during this time, how it relates to the rifting of Rodinia. We don't have a rock record to tell us that, but we do have the basement rocks that are available to us to sample and hopefully learn more about. So I have a proposal in right now with my colleagues at Montana State and Columbia University to try to do some of this exciting thermochronology right in our backyard here. We have the potential to learn more about Western Laurentia's rifted margin and exactly how the rifting of Rodinia happened. This was also a time period, the Proterozoic, where there were profound transitions in Earth's climate as well as life. And then there's this persistent question of, what is the role of ancient fault zones in recent mountain building? The topography that we know and love in the Northern Rockies, in what ways does it have its origin in ancient mountain ranges that have been reactivated over and over again? So stay tuned on that. Maybe invite me back in 5 or 6 years. And if I'm lucky, I'll have some things to say about the rocks in our backyard here. With that, I'll just kind of throw my conclusions from the Front Range part of the story back on the slide. And I'd like to thank you all for joining me this evening, and I'd be more than happy to take questions.
This is Mike. Kendra, thank you very much for a fascinating talk. But we're going to ask you to come back sooner than 5 years, I'm afraid. So
Uh-oh.
I hope we can work that out.
That would be great.
Yeah, and maybe even in person. So we do
Oh,
have a
that would be
number.
so fantastic. Yeah.
Yeah, we do have a number of questions, and so why the some zircon crystals in the same rock sample have different amounts of uranium and thorium, and how does that work?
Oh yeah, that's a great question. So the amount of uranium and thorium in the zircon crystals depends on the conditions when that crystal was actually growing, normally in a magma chamber way back when those igneous rocks, for example, were growing. And so when there are changes in the composition of the magma, you can have changes as a result in the composition of the zircon. And so there could be those types of processes. It's even more common in rocks where you have not maybe an igneous rock, but you have a metamorphic rock, especially one that maybe started its life as a sedimentary rock. So then you'd have zircons coming in from different original rock types that would have a wider range of compositions because they grew in wildly different magma chambers at different times in different places. And so actually one of the challenges of doing this is we get the most information from a rock that has a really wide range of compositions because we want that trend. And so it's very commonly, especially with igneous rocks, you get kind of a narrow zone. And so sometimes we'll combine several samples that have different ranges of compositions in order to try to get around that problem. That's a great question.
Another question is the great unconformity in the Grand Canyon and the greater unconformity here in the Tetons. Could you explain the difference? Because it's a fairly large time differential between those two great and greater unconformities.
Yeah, so there are two reasons why the one in the Tetons is greater. The first reason is that the basement rocks in the Tetons are much older than the basement rocks in the Grand Canyon. So in the Grand Canyon, those basement rocks, they crystallized, they formed about 1.7 billion years ago. Whereas the basement rocks we have in the Tetons, they're a billion years older. They're around 2.6 or 2.7 billion years old. And so that right there adds an extra billion years to the gap. And then in the Grand Canyon also, there are some sediments, depending on exactly where you are, that are actually also Proterozoic in age. So rather than waving my arms around, I can actually just go back to my little cartoon. Me one moment. Here we go. Yeah, so these blue rocks here, this is the equivalent of what's sitting on top of Mount Moran or on the Wyoming side or on the Idaho side of the Tetons. But in some places in the Grand Canyon, you can see they're actually these older sediments. And we can tell they're older because they have, they've been tilted and then beveled and additional unconformities on top of them. But some of those are also pretty old Proterozoic rocks. And so that also contributes to not missing as much time. The record in the Grand Canyon is more complete than it is in the Tetons.
Could you just re-emphasize the time span of the great unconformity in which you're talking about, and please answer that question first, then we'll get to the next one.
Yeah, so the great unconformity in the Tetons, 2 billion years is about 40% of Earth's entire history. So the Earth is about 4.6 billion years old. And so when you're missing that much time, it's just so much happened during that time that we don't have a record for. And in fact, actually for several generations of geologists, there's then been this kind of persistent idea that the Proterozoic is boring. It's something called the boring billion, because really, it probably wasn't boring at all. There was probably all this really cool stuff going on, but it seems to have mostly been lost in the rock record. There was erosion that has removed all of that record. And so we don't really know what was happening during that time. And now that we're getting these windows, these pieces of information with methods like this, we're starting to really reveal how interesting that part of Earth's history is, even with just the small pieces of it that we get to see.
So what is I'm just going to read this one. What is the reason why the Nemaha uplift has high helium concentrations? And that's NEMAHA, because I may not be pronouncing it correctly.
Yeah, so I'm not familiar with that uplift, but there are a couple of reasons why we could have high helium concentrations in rocks that I could talk about, and perhaps this would help. So helium helium-4, which is the helium isotope that I study, is the product of radioactive decay. It's that alpha particle. And so in places where there are lots of very old basement rocks, those rocks have a lot of helium in them. And so if you go to those places, there's actually a lot of helium just kind of coming out of the rocks. And once it comes out of the minerals, it goes into the atmosphere, and I think even out into space. Like, it doesn't really stick around. But that's one reason why you might have a lot of helium. Another reason is actually the other isotope of helium, which is helium-3. So helium-3 is not the product of radioactive decay. It is actually a primordial element, and it's incorporated into the Earth at the formation of the Earth when our solar system formed. And so there are places where you can go where that helium that's primordial is actually coming out of the mantle. And you can measure it. And so we'll look at the ratio between helium-3 and helium-4 in places like Yellowstone to try to fingerprint where we're actually getting material coming from deep in the mantle. And so that's, not related to this type of helium work, but it's another application of making measurements of helium in Earth materials.
Excellent answer. So just to sort of review and confirm, the global unconformity, this huge unconformity, is a global event that you see not just in Western North America. And that would seem to tie in very well with the Snowball Earth hypothesis as a means of creating this unconformity. In other words, removing a couple 100 million years of rock, which is only a part of the unconformity, but still it provides part of the answer. Is that a good interpretation?
So I'd say that's one interpretation. I think that the great unconformity has been this kind of persistent puzzle for a long time. And as I said, a source of consternation amongst geologists that we don't have more of a record. And then this paper that came out a few years ago by Brian Keller and all, who suggested that, maybe the great unconformity actually represents an event, a global event. That is a pretty new idea, and that is one idea. However, I would say there are groups of people pushing back pretty hard on that idea, that you just have so much time to work with that there are all kinds of things that could be happening over the billion years or 2 billion years that are missing here. In some places, it could be the lack of a rock record. In other places, it could be erosion moving things around. Some people also think that actually this breakup of the supercontinent Rodinia might be the event that triggered a lot of erosion across and kind of making the great unconformity what it is. And so I think this is an area of active debate right now. And there are people like me generating these data sets in various places and then arguing about, is it climate or is it tectonics? Like, which of these things, or maybe it's a combination of both, which is usually the answer, right? So I think my answer at this point is stay tuned. I think we're about to learn a lot about this over the next decade or so, as a lot of us wrestle with these complicated data sets and how to best interpret them and what they can tell us about this period in Earth's history. But I think, the observation is that we're missing a lot of time, and it could be related to a single event. That's kind of a nice kind of satisfying way to think about it. But it could also, because we have so much time to work with, be tectonics here and a glacier over here, and other things kind of together making one unconformity in the end.
So it would seem like the great unconformity is long enough that it could actually be associated with perhaps 2 supercontinent or Pangea Rodinia type Columbia events. Is that correct?
Yeah, I'm trying to remember going even further back. There are the further back we go, the harder it is for us to pinpoint the supercontinents, because they just get all dismembered and moved around. But indeed, I think that this, the idea that one unconformity today is actually many unconformities all stacked on top of each other is certainly true. And I'm sure there are places that the great unconformity represents multiple phases. In fact, let's just think about the Canadian Shield, where today we just have all these basement rocks exposed over a huge area. there's an unconformity that represents both Rodinia and Pangea, right? And it's still an unconformity today. It's not actually an unconformity, it's just a surface because we don't really have sediment sitting on top of it at the moment. But yeah, I mean, that's one of those persistent basement exposures that's really quite spectacular when you think about how much time it represents.
Right. And in your first slide, now that I know what your talk was, I think John should have labeled the dike running through there, which is associated with the rifting that broke up Rodinia, which is a key part of your talk.
Yeah. No, this is a spectacular dike.
Yeah.
Yeah, no, it's great. And actually, so technically right there, the great unconformity is much shorter, right?
Yes, exactly. Yeah, by 500 million years or so.
Yeah, plus or minus.
Right. And so last question, the technology you're using and the techniques, can this help inform us about the general uplift that has occurred in Western North America in the last, say, 12 million years or so, where things have gone from sea level to, a mile plus high across an enormous part of Wyoming, Colorado, Utah, Montana, Idaho?
Yeah, that's a great question. And my PhD was looking at the Colorado Plateau and then using these techniques in much younger timescales to think about that landscape's history. So it can help us, but in an indirect way. So this is because the systems that I'm talking about, they're responding to the cooling off of rocks, which in order to do that, we actually have to move the rocks closer to the Earth's surface. And so our systems are not sensitive to the elevation of that surface. And so if uplift was also accompanied by erosion, which it commonly is, then yes, we might see a signal of rock cooling, but we'd have to make an interpretive step. We'd have to say, okay, the rocks are cooling off. Perhaps that's because the elevation is changing and that's causing erosion to happen. And therefore our rocks are cooling off. And so it's not a direct comparison. It's not a paleoaltimeter. It can't tell us how high an elevation was in the past, but it can tell us how far below the Earth's surface a rock was in the past. If that makes sense.
Well, again, I want to thank you for an excellent talk, and we do look forward to having you come here in person and present more research. I think 2 years is probably a fair amount of time. And I want to remind everyone that on May 3rd, Laura Vieta will be here to talk about tapirs, not very far. They probably were here as well as down in Kemmerer during a very different climate in Wyoming's past. So Kendra, thank you very much. We really appreciate it, and we hope to see you in person soon. And I just want to say good night to everyone, and we'll hopefully see you in person in the library on May 3rd, or if you prefer on Zoom. Thank you, everyone. Good night.
Thank you.